In this session, we are going to discuss about the power spectral density of a non-return to zero unipolar technique. So, like here, we will discuss a few more steps that how can we calculate the power spectral density. Before that, we need to know which are the steps for that. So the first step is to calculate Fourier transform of non-return to zero pulse x of f. Second step, you need to calculate autocorrelation of the unipolar pulse r of a and n. The third step, then you can calculate power spectral density based on the above two calculations. For example, we have discussed and we have seen the non-return to zero pulse remains high for the bit duration. So, like this is given that the amplitude is 1 and it is high for the bit duration x of t. You can represent this same pulse with this pulse, like from minus TB by 2 to TB by 2. So the average is still TB and it remains high for from minus TB by 2 to TB by 2. So that is NRZ unipolar pulse. The first step was that to calculate the Fourier transform. So we know the basic formula of the Fourier transform, that is the integral from minus infinity to infinity x of t e raised to power minus j2 pi f of t dt. So we if we use x of t, the amplitude of x of t is 1 and the limits are from minus tb by 2 to tb by 2 and the remaining is the same thing. And if you take the integral of that one, then you will end up with this type of calculation. Like these are the just taking the integral and then applying the upper and lower limit, and here we are uh, because it is negative sign and this is negative and the limit is negative, so it becomes positive. So we will write first the positive value and then taking the negative as a common, so negative and negative cancel out and we have the remaining negative. And we know the simple Euler formula, that is sin theta is equals to a raised power j theta minus e raised to the power j theta divided by 2j. So if we use this formula here in this equation, so the answer x of f will be 1 over pi f sine pi f tb, because here the extra term is 2j, so it means that we have to multiply it by 2j. So 2j will be cancelled out with this 2j, so that is why it is 1 over f sine pi f tb. So the remaining, because this is f db pi and 2j will be cancelled out. So if we need to translate in term of a sinc function, so if we want to translate this function in term of sinc function, then it means that you have to multiply and divide by tb, so that you can have extra term here tb. So because sine pi f tb, so pi f is already there, so tb is missing. So you can divide and multiply it with the tb. So sine pi f tb divided by pi f tb multiplied by tb, and we know that the sinc theta is equal to pi sine pi theta by pi theta. So that is why it is tb f uh, sinc f of tb. For unipolar, we know that al is equals to a if the symbol the amplitude is equals to a if the symbol is 1 and 0 if the symbol is 0. We have already calculated the Fourier transform. The second step is to calculate the autocorrelation. So for that we are just assuming the value of the amplitude. So for a binary sequence, and you know that in a binary sequence you have two bits, either 0 or 1. So for 1 you have the amplitude A and for 0 you have the amplitude 0. So it means that if the bits are 2 and both bits are equiprobable, then the probability of occurring A is equal to the probability of AL is equal to 0 is half, because the you have two bits, so then one probability of each is 1 by 2. And autocorrelation R of A and N is equals to the estimation of AL multiplied by the shifted version. Of AL. So you can write AL multiplied by AL minus N. So you can consider various cases. Like let's assume if n is equals to 0. So if n is equals to 0 and you insert here n is equals to 0, so it means that R of A n is equals to 0. Estimation of AL multiplied by AL, the answer will be AL square. And you know that the estimation of the continuous function, if it is a continuous function, you can write in term of integral x square f of x dx. But if it is a discrete function, you can write estimation in term of summation. So summation of x square probability of x. So we have two bits 0 and 1. So AL, if it is 0, so AL is 0 and AL is also 0 and AL square is 0 and the probability is 1 half. But if it is 1, so then AL is 1 and similarly AL is A, and then if you square this, then the multiplied by A, the answer is A square, and its probability is also 1 half. So you can calculate the probability estimation for these things. So estimation of AL square, so that is the autocorrelation when n is equals to 0. So it means that AL square, so which that is x square, and the probability when x is equals to x. So AL square is A square. The probability of AL when it is equals to A plus the second is 0 multiplied by probability when AL is equals to 0. So this term is cancelled out, and the probability of when AL is equals to A is 1 by 2. So that is why autocorrelation when n is equals to 0 is equals to A square by 2. But suppose if n is not equals to 0, so then it means that you have four different possibilities. First one is 0 0, the second one is 0 1, and the third one 1 0, and the fourth one is 1 1. For all these probability, we can calculate AL and AL minus n, so, and AL multiplied by AL minus AN. So here, because n is 0, so that is why AL minus n is equals to AL, because n is 0. So that is why this term looks like similar to this term. But in the second case, when we assume n is not equals to 0, then the estimation will be equals to AL multiplied by AL minus n. And for all the possible four possible combination, we can say if it is 0 0, so AL multiplied by L minus 1 is 0. The probability of each is, because we assume equilikely symbol, so that is why the probability of each will be 1 by 4. The other condition A 0 and 1. A, so if you multiply 0 with A, the answer is 0. A 0, if you multiply it by A, the answer is 0. A, and if you multiply it by A, the answer is A square, and the probability of each is 1 by 4. So now in this case we can calculate the estimation. So the estimation when L multiplied by AL minus 1, the shifted version of that one, or you can say autocorrelation when n is not equals to 0, that is equals to the summation of x square. So it should be x square multiplied with probability of x. So if you are using same step as we have done in the previous, like the same step that we done here in this page, like when you calculate the estimation, we use these steps. So if you're using these use these steps in this equation, and then you can also end up with this result a square by 4. So the autocorrelation for both cases you have already calculated. So a square by 2 when n is equals to 0, when n not equals to 0, it is a square by 4. Third step is the power spectral density. So we use a uh, Wiener-Khinchin relationship in order to calculate the power spectral density P of f, which is equals to 1 over Tb, the amplitude x of f square multiplied by summation from n minus infinity to infinity autocorrelation multiplied by e raised to minus j2 pi f of n t b. So you can just insert the values that you have calculated in the previous page, value of x-axis and value of autocorrelation, and just simplify. So you can see you will end up with this answer. And then here, so you are using n not equals to 0. So if you remove n not equals to 0, and so you can just write minus 1, and then you can remove n not equals to 0, and this mission sign is this one. So you multiplied that one, so multiplied by this with this value, and then multiplied by this with this value. So it means that you have a, for this one, if you multiply it by this one, you will have 1 by 4, because this is and this is same, only the amplitude is different. Like it is 1 by 2, it will be minus 1 by 4. So you can say 1 by 2 minus 1 by 4 LCM, and then 2 minus 1 by 4, the LCM is 1 by 4. So that is why you can simplify this term in this format, like a square tb by 4 sin square f tb plus a square tb by 4 sin square f tb, and then multiplied by this mission sign e raised to minus j2 pi f n tb. So you can simplify this by using the Poisson formula, where e raised to j2 pi f and tb is equals to 1 over tb and the delta function. So you can use this formula in this equation, and you can write the power spectral density in this format. So we are just writing the same thing. We are just implementing the Poisson formula and calculating that this will be the. So it means that you have this sinc function multiplied by the impulse function. So how can you draw the graph of this calculation? So here, like you can see, so this is the sinc function. So this is the sinc square function. So 0 TB, 2 TB, 3 TB, 4 TB, minus 2 TB, minus 3 TB, and minus 4 TB. And this is the impulse stream. So you can see each like TB, 2 TB, 3 TB, and 4 TB, you are getting some amplitude, but these amplitude are multiplying with the null values of this sinc function. So if it is multiplied with the null values, so it means that this whole portion and this whole portion from minus TB to minus 4 TB, they are cancelled out. Only you have this term. So it means that if you multiply that with this, so you will end up with this function only. Sin square f of TB multiplied by the delta function at f. Okay, so if you use this value in your previous equation, you will end up with the power spectral density a square tb by 4 sin square f tb plus a square by 4 multiplied by this delta function at this point. So it means that this extra term is basically the DC component, which is leading to the distortion, but it can be minimized, or it can be removed by using different techniques. This was the power spectral density. So let's do one example to understand uh, its usage in the techniques. So the example is that a communication channel of bandwidth 75 kilohertz is required to transmit binary data at a rate of 0.1 megabit per second using raised cosine pulses. You need to determine the role of factor alpha. So given information is bandwidth, BT is equal to 75 kilohertz, bit rate which is 0.1 megabit per second, and for raised cosine pulse you need to calculate role of factor. So the power spectral density of raised cosine pulse is given in this, like if you want to see the graph of the power spectral density of raised cosine pulse, the graph look like this one, and then from here to there it is half of the bit rate, and this slope, this slope is basically explain the role of factor, and the range of the role of factor is vary from 0 to 1. So we know the formula for that one. The bandwidth is equals to 1 plus alpha multiplied by RB divided by 2. And you want to calculate alpha, so it means that you need to rearrange this equation. So take the alpha value on the other side, so 1 plus alpha, and then this 2 multiplied by bt, and then this will be the denominator. So alpha, and then this minus 1. So you can use all the values, all the data is given. Bandwidth is 75 kilohertz. Data is zero point 0.6 into 10 to the power of 6, zero point 0.1 into 10 to the power of 6, and then minus 1. So if you're using calculator, you use, so this value is equals to 1.5 minus 1. So the roll off factor is zero point 0.5, that is within the range 0 to 1. In some question or in some example, data is rate is not given, but usually the bit duration is given. That is TB. So if the bit duration is given, you can calculate the bit rate, like, or the data rate RB, that is equals to 1 over bit duration. So that's all for this session. I hope you understand the power spectral density calculation and the example. But still, if you have any question, you are most welcome. You can ask the question in the comment box, and we will try our best to answer the question. Thank you for watching the video.